Suppose F is a field. Let F star denote the set of all non-zero elements of F. And so F star is a group under multiplication. It turns out that subgroups of this group, finite subgroups of this group, are all cyclic. Theorem: let F be a field then any finite subgroup of F star is cyclic. Before we go to the proof, let me just give you some examples. So if you take the complex numbers, then you look at C star, then every finite subgroup of C star consists of Hn equal to e to the 2 pi I k by n, where 0 lies between, k lies between 0 and strictly less than n. These are the nth roots of unity. In fact, when we prove this theorem, we'll see that it's a very similar situation there, that if we have a finite subgroup of F star of order n, then it consists precisely of nth roots of unity. So let's prove the theorem. Suppose H is a subgroup of F star and cardinality of H is equal to n. Then by the structure theorem for finite abelian groups, we have that H is isomorphic to Z mod D1 cross Z mod D2 cross Z mod Dk, where D1 divides D2 divides Dk, and the additional fact that the size of H is n means that D1, D2, the product of these things, is equal to n. Okay, now note that every element of H satisfies x to the power dk is equal to 1, because the order of each of these cyclic groups divides dk. And so what we have is that every element of H is a root of the equation of the polynomial t to the power dk minus 1. But this polynomial can have at most dk many roots, because it's of degree dk. And so we have that n is less than or equal to dk. But this is only possible if n is equal to dk and in fact k is equal to 1. Or I would just say n is equal to d1. So i.e. H is isomorphic to Z mod. Okay, so that concludes the proof of the theorem. Every finite subgroup of the multiplicative group of any field is cyclic. In fact, if it is of order n, it is isomorphic to Z mod n. So now let's look at finite fields. So the multiplicative group of finite field. So theorem, and this actually is an obvious corollary of the previous result. If so if E is a finite field, if E is a field of order p to the n, then the multiplicative group of E is isomorphic to the cyclic group Z mod p to the n minus 1. Proof? Well, E star is a finite subgroup of E star? Well, it's the full group, and it's finite because E is finite, so E star is finite, and so the previous theorem applies, right? So E star has to be cyclic, and its order is p to the n minus 1, so it's a cyclic group of order p to the n minus 1. So upshot of this is that E star can be written as 1 alpha alpha squared alpha to the power p to the n minus 1. You can pick an element alpha, a non-zero element of the field, such that every element of the field can be written as a power of that original element. Okay, so that's a very powerful property, and we'll see some applications of that in the next lecture.